Today we're going to cover what time complexity is, and I think this is actually one of the most important things to learn before going into data structures and algorithms. So we are used to solving problems, can make our solutions, but oftentimes I feel like, especially when you're starting out coding, you just know how to solve the problem and that's it. We're not concerned about time complexity or even about space complexity. And if we look at our solutions, sometimes I think, well, at least for me at first, I wasn't able to figure out what the time complexity was exactly when I even coded the solution myself. So I think big O notation is important in regards to how we code and how we think about our code. So first, let's go over what time complexity is. Time complexity is expressed using big O notation, and these are our big O notation over here. It is used in computer science to represent how long an algorithm takes to execute or describe the performance of an algorithm. Big O notation represents the worst case scenario. So what is time complexity? It basically measures performance. And there are 7 cases for big O notations. First one being constant and last one being factorial. Constant is actually the fastest and factorial is the slowest. So it goes from fastest to slowest. And there are a few things to consider when you consider your big O notations, and there are 4 of them. First one is assume the worst case, and that's actually a part of our definition itself. So there are actually 3 cases. First one being best, second one being average, and third one being obviously worst. So for example, let's say that we have an array with 5 elements. So 5, 4, 1, 3, 2. We want to look for the number 5. If you look at our array, 5 happened to be the first number in our array, right? So that means that after first iteration, you don't even have to loop through the rest of the array. We know that the number 5 is at index 0. So this is our best case. But what up for number 2? So number 2 is at the end of our array, right? So in order to find the number 2, we would have to iterate the whole thing. So finding or looking for or searching for number 2 will be our worst case. And we want to always assume the worst case because whatever the number that we are looking for, we don't know where it is. But we know at least that if we iterate through our array once, worst case, we're going to find it at the end of our array. And second rule is remove constants, remove repeated measurements. We want to remove repeated constants. So for example, let's say that we had 2 loops. If you're not too familiar, that's fine. It'll be O of 2n, right? So we want to remove this constant and make it into O of n because this allows us to get more clear understanding of big O. It's more simple. It's still O of n. And third one is different terms for inputs, input of different sizes. Okay, this one will have another example for these 2 as we go through our code, but just to explain the third one, let's say that we have an array A that has a length of 5 or an array B that has a length of, let's say, 10, and we're looping for both of them in one function. So loop for loop length 5 and for loop 10, and these are 2 different for loops in one function. So we know that this is O of n and this is also O of n. So does that make O of n plus O of n, which is equal to O of 2n? And we remove constants, remember, right? And does that make O of, actually it doesn't, because we know that the input size of A and B differ, right? So first one being 5 and second one being 10. If it was the case that the length was 5 for each, this will hold correct. But because the input sizes differ, we have to consider them as 2 different ones. So it will be actually O of A, because it's array A, plus O of B. And this is going to equal to O of A plus B. And I actually have an example just for this. If you don't get it right now, that's fine. And last one is drop the non-dominance. So if you're familiar with math class in your middle school or high school, x squared plus 2x plus 1,000. And let's say that our x was really huge, for example, like 1,000,000. 1,000,000 squared is like some huge number. I don't even know what it is. And obviously this is going to be 2,000,000. And our x is really big. Does 1,000 really matter? No, right? 1,000 is gonna be like nothing. If we have 1,000,000 squared, is 2,000,000 gonna be a huge number that compares to x squared? No, it's not. So we disregard this. And that's the reason why we only think about the dominant term. So we're going to get rid of these two elements and just look at x squared, which is kind of like n squared in this case. So drop the non-dominants, only look at the dominant terms. Now let's go for our first big O, which is constant. And remember, this is the fastest big O out of the 7. So what is the definition of constant time algorithm? Constant time algorithm will always be executed in the same amount of time. So this is important. Always be executed in the same amount of time, regardless of the input size. To simply put, input size does not matter. Only one operation is performed. So I have an example over here. I have a function named constant, and I just gave a bunch of different input sizes. So 10, 100, 1,000, and 10,000. And also, I have my constant function, which takes in a number, and I declare a few variables. So this performance class, it just tracks how long the code between this T0 and T1 runs, how long it takes to execute. Now, we know that for constant, our input size does not matter, and only one operation or execution is performed, right? So I have my variable that's going to count how many executions this function runs, and kind of think about what our number of execution is going to be for each input. Well, we know that our input size does not matter, and we're gonna do only one operation, so we expect to get only one for all the inputs, right? So I'm going to make a code that demonstrates a constant time complexity. First thing I'm going to do is I'm just going to increase execution by 1, and let's just console log n, and I'll return that later. So if we were to run our code, you can see that our output or number of executions were all 1. So it did not matter if we had an input size of 10 or 10,000. Our code runs only once. So that is constant, and that demonstrates how constant function performs. So again, input size does not matter. Only one execution or operation is performed. Now let's try to calculate our big O. And for the purposes of the simplification, let's just ignore this declaration of T0, T1, and console log of T1 minus T0. And remember, again, this just tells you how long the code ran for. So the first one is input of 10, 100, 1,000, and 10,000. And just keep in mind that the first operation or first few actually takes a while to execute, because it takes a while for this program to start up, and that's why you have a bigger number for the first one. What if we were to just copy this and paste? And you can see that the second one, which had same number of input, is 0.13, which is kind of similar to all the rest of the performance of this code. So keep that in mind. Now let's figure out our big O, and let's start with our first declaration of our execution variable. Well, for declaring variables, this is a O of 1 operation. So O of 1. And for this one, we're incrementing our number, right? And how many times do we do that? We only do that once. That's also O of 1. And this one is also O of 1 because we're simply just printing out the number n once. And our last one is our return statement. And return statements are also O of 1. So we have how many O of 1s? 1, 2, 3, and 4, right? So that's going to be O of 1 plus O of 1 plus O of 1 plus O of 1. And if you sum this up, it's going to be O of 4, right? So this is our time complexity. We are actually not done yet, because remember, what was one of the rules for simplifying big O's? It's that the rule is that we want to get rid of constants, right? So we're going to get rid of this 4 and then just replace it with O of 1. And as a result, our final big O is going to be O of 1 for our constant. If you guys find this helpful, make sure you guys like and subscribe. Thanks. Now let's go over our second big O, which is logarithmic. And logarithmic has big O of O log n. So what is definition of a logarithmic time complexity? Logarithmic algorithm is proportional to the logarithm of the size of the input. So this is a more of a mathematical definition. So if you didn't get that, that's totally fine. It means that as input goes up exponentially, so as input goes up like crazy, time goes up linearly. Time goes up straight. The execution time increases at a decreasing rate. So at first, when we have a logarithmic time complexity, and if we have a crazy big input size, at first it's going to be really steep. And then as our input size gets bigger and bigger, it's going to flat out. And if you remember our big O graph from before, it goes something like steep and then it kind of flats out like that. That's what it means to increase at a decreasing rate. So these two are more of a simpler illustrative, I'll say, definition. So half the number of loops each time we go through the loop. So what we're doing is we're halving number of times we can loop through our array each time we go through our loop. So another one is number of times we can cut the number in half. So let's say that our input was 8. How many times can we cut this in half? Well, if you cut it in half, at first it's gonna be 4, then 2, then 1. So we were able to cut this number in half by 3 times. And that's what it means to have a logarithmic big O. Now let's try coding our example. So what I'm going to do is make a for loop. Let I is equal to 1, I is going to be less than n, and we're gonna multiply our I by 2 each time, because remember, if you were to have the number of loops each time, we want to multiply it by 2. And we start at index of 1 because what happens if you multiply 0 by 2? You get 0. So this would never end. And inside that loop, I'm just gonna increment execution by 1 each time. So this execution is count how many times our function runs. Okay, so you can see that when we had the input of 8, it was 3, 10 is 4, 100 is 7, and 1000 is 10. And compared to our constant, which was 1 for all the inputs, it does get bigger, right? As our input size increases, our number of execution does increase. And here you can also look at the performance. And well, compared to the first few, obviously logarithmic here is faster, right? And again, that's because when this program starts firing up, the first few takes a little while to, I guess, compute. So that's why it gets bigger performance time. Now going back to logarithmic, let's figure out our big O. And let's start with our execution. Well, like before, declaring a variable is O of 1. And we know that from previous, this is also O of 1. And well, we're incrementing our execution here. So this must be O of 1. And how about our outer loop? Well, this is going to be O of log n, right? Because we're having number of loops each time. And if you were to just look at how I compute, it's, all right, let's comment out these 4, is 1, 2, and 4. And this is exactly what we have. 1, 2, 4, and then our 8 was our original number, which is right here. Okay, now our final calculation for our big O. So we have how many big O of 1s? 1, 2, and 3, right? So that's gonna be O of 3 plus O of log n. Well, we exactly don't have O of 3 because this O of 1 is inside our loop, right? So technically, it's actually O of 2 plus O of log n times O of 1. But we can get rid of this because if we were to multiply this out, it would still be O of log n. So going forward, we're not going to count this operation. And again, this is still O of 1, but still, we can get rid of this in our calculation. Now, we have O of 2 and O of log n. And remember, we have to simplify our big O. And what was our rule? We want to only keep the dominant term. So O of 2 is less dominant than O of log n because this is constant and this is logarithmic. And logarithmic has a higher precedence. So we're just going to keep log n, and that's how we get our big O for this one. Now I want to go over another example for logarithmic time complexity, and we're going to use binary search to do that. If you're not too familiar with what binary search is, what it does is it looks for a value, in our case 1, in an array, and is going to point to the middle index. So we have 8 elements, and if we were to round down, our middle element would be 4. So it's gonna look for this middle element and it's gonna compare 1 to 4. If 1 is less than 4, it's going to look at array on the left, and if it is the other case, it's going to look at the array in the right. and then it's gonna keep doing that until we find our number that we want and return that index. So what we're essentially doing is we're halving the number of arrays that we are looking at. One key point is that the input has to be sorted. So our array has to be sorted in order for binary search to work. So I have an array with 1 through 8, but this does not have to be the case. We can have like other numbers, it just has to be in order. So essentially halving the number of operations each time. So like I said before, we look at number 4. Is 1 smaller than 4? Yes. So we're gonna look at our left array. And now is 1 less than 3? Yes. So we're gonna look at other half of the array. And then lastly, we're gonna look at it individually, and we find our number 1 and return that index. So we are having the searching array each time. Now this is our pseudocode. You can read it and then try it on your own if you want. And I have our value, which is v. I have our array, and I have my left index, which starts at 0, and right index, which is the last one. Okay, first thing I'm going to do is I'm going to make a while loop. So while left is less than or equal to right, left is less than or equal to right, I'm going to declare a variable const, and I'll just call it m for our middle index, and I'm going to round down. So math.floor, and if you want, you can round up to, it's totally up to you, and it will be L plus R over 2. So we're finding the middle term by adding left and right index and dividing it by 2 and then rounding it down. Now I'm gonna check if value is equal to array at index m. What are we gonna do? We're gonna just return m. Now it's our next if statement. What if our value is less than the middle element, which is 4? Well, what we're gonna do is else if value is less than array at index m, I'm going to reset the right index to middle index minus 1. So right is going to be m minus 1. Now, why do we do that? At first, our right index is all the way at 8, right? And we looked at 4 and realized that 1 is less than 4. So we want to look at only the elements left of 4. So our 4 is represented by index m, and if you wanted to look array left of the number 4, we would do m minus 1. So m minus 1 would refer to this index, and that way we could look at only this array. So L is still gonna be 0, but now we reset our R index to be this one, so we don't have to go through the whole thing. And now our next one is the other case. If value is greater than array at index m, what are we gonna do? We're gonna reset our left index, and this will be m plus 1. So this would be the opposite case, right? What if our value was greater than 4? We want to look at this side of the array, right? The right side. And now we want to reset our L to start here, and we're gonna keep our R index to be the last one. And actually, you don't even need this else if statement because we can just write else just to make it simpler. Now it's going to be our last line, return minus 1 if value is not found. So we're gonna return minus 1. If this does not find the element, it's going to return -1. So our value was at index 0, so it returned index of 0. What if our value was 2? It's gonna return 1. If it was 8, it's gonna return 7. What if it was -1? It's gonna return -1 because it couldn't find the element in our array. So it would be the same for if our value was 10. So still -1. So this is binary search, which has a big O of log n. And remember, the reason is because, and this is the more important thing, we are halving the number of operations that we do, and we are only searching the other half of the array each time we go through our while loop. Now let's go over our linear time complexity, which has a big O of n. So what is a definition of linear time complexity? So linear time algorithm will increase directly proportional, this is important, to the size of the input. As the input size increases or decreases, the time complexity will increase or decrease proportionally. So what does that mean? It means that if our input size increases by 1, our time complexity will also increase by 1. Simply put, time increases directly proportional to the input size. We have our linear function and we have our inputs 10, 100, and 1000. When we have a linear time complexity and if we have an input size of 10, our linear function will do 10 executions, so 10 operations. If it has 100 inputs, it's going to do 100 executions. 1000 is going to do 1000 executions. So let's see that with code. I is going to be less than n. We're gonna increment by 1 each time, and what we're going to do is same as always, increase execution by 1 each time. Now, like we said before, when we have an input size of 10, our execution is going to be the same. When we have 100 executions, 1000 and 1000 executions. Now, what if we were to now figure out our big O? So like before, this is O of 1, simply declaring a variable. This is also O of 1. And lastly, this is also O of 1. Okay, how about our loop? What is our loop going to be? Well, it's going to be O over n, obviously. The reason is we're looping through this for loop n number of times and then doing n number of executions. Now, let's calculate our final big O. So it's going to be O of 1, 2, and I forgot to mention before for my logarithmic problem, this is also a O of 1 because we're declaring a variable here also. So that's going to be 1, 2, and 3. 3 O of 3 plus is going to be O of n. And remember, we said we don't calculate this n because essentially it's O of 1 times O of n, which is still O of n. So going forward, we're just gonna ignore this. And what's going to be our final big O? Well, this is a non-dominant term, so we get rid of that and we just keep our O of n, and our linear time complexity is going to be obviously O of n. Now let's go for another example for linear complexity, and the function's name is half loop. Now like before, I have execution variable and we're returning that, and I think we went over this enough times and we know that it's going to be O of 1. So I'm just going to leave it like that going forward. For this one also, we're going to make a for loop that I is equal to 0. I is going to be less than n, but this time we're going to increase I by 2 each time. So essentially we're doing half of the number of loops. And like before, execution increment by 1. So you can see that we literally just did half of the loop, right? When input was 10, our output or number of executions were 5. But how are we supposed to find out the big O for this one? Is it gonna be O of n, logarithmic, constant? Well, it's obviously not gonna be constant, and it's actually going to be, as you guess, linear. And let's go over the reason why. Why is half loop O of n when for our previous example, our execution was 10 and that was linear? Why is it the case that when our input is 10 and our execution is 5, why is this linear too? So we have O of 1, O of 1, and this I is also O of 1. So we have O of 3. Now for our for loop, this is also going to be O of n. And if you thought wait, that's actually wrong. It's not O of n. This is actually O of 1 over 2n, which we can rewrite it as O of n over 2 because we're doing half of the loops, so n over 2. And this differs from logarithmic because in total for this one we're doing half of the loop, but logarithmic, each loop we're doing half of the other half that we did. So we have our O of 3 plus O of n over 2. Now we know that we can get rid of our non-dominant term and get rid of O of 3, but how about this one? Why is our final time complexity O of n? Well, remember, we can actually rewrite this as 1/2 times n. So what is 1/2? Well, 1/2 is actually a constant. And if you remember from our rule, we can get rid of our constants, right? And this is what we're going to do exactly. So we get rid of our constant and we just keep that n, and we finally end up with O of n. So this is why it's not half n, because we want to simplify and get rid of our constant. So we designate this time complexity as O of n. I actually have another example for linear time complexity, and this function is called toLoop. And I made this function because I want to illustrate another example, which was part of simplifying our big O. And if you remember, I think the third one was that we have to consider inputs of different sizes. So we take two parameters, which is array A and array B. And as you can see, array A has a length of 3 and array B has a length of 6. So let me illustrate what I mean by sizes of, or inputs of different size. So like our typical for loop, I'm going to make a variable let I is, or for loop, I is equal to 0, I is going to be less than array A dot length, and increment by 1 each time. And like before, I'm just going to increase execution by 1. And I'm going to have another for loop, let I is equal to 0, I is going to be less than array B dot length. So I'm iterating through array B, increment by 1 each time, and increase execution by 1 like before. So is the 9 the number of executions that you expected? If that is so, that's great. But more importantly, how do we figure out our big O? That's our primary concern. So let's start with the easy ones. We have O of what? We have this line, we have our execution, we have our declaration of I, another declaration of I. You can change this to J if you want to get rid of some confusion, but still, we have O of 4, and that's all our constants. And for our for loop, this is going to be O of n, and this is also going to be O of n. So we have two O of n's, right? So that's going to be O of n plus O of n. And we know that we can get rid of our non-dominant term, which is constant. And finally, we have O of 2n. Well, again, this is another constant. So we have O of n as our final big O. And if you thought it this way, that's okay, but this is wrong. And let's go over why this is wrong. That's more important. So this is wrong. Exclamation mark. Well, our big O is going to be the same for the first one. It's going to be O4, but our time complexity for these loops are going to be more, well, it's going to be different. And we know that our first for loop runs array A length of times. So that's 3 times. So let's just say instead of n, let's just say A. And for the second one, this one runs array B length of times. And let's just say that this is B. Now, if we were to come back to our big O, it would be O of A plus O of B, right? So this one kind of makes sense. O of A represents how many times we loop through our first array. O of B represents how many times we loop through our array B. Now, like before, we can get rid of our non-dominant term, and we are left with O of A plus B. Now, how did we end up with O of A plus B? Well, again, going back to our third rule, we have to consider the inputs of different size. And our input sizes are 3 and 6. And if you add up 3 and 6, we get 9, right? So we did total of 9 executions. So our toLoop function had 2 for loops, which wasn't nested. So it's not nested. And it's going to do A number of executions, and then it's going to do B number of executions. So this function in total does A plus B number of executions. So if you were to write O of n, what would n represent? Would it represent 3? And if it did, that means that our for loop is going to run only 3 times. Our execution is going to be 3, but that wasn't the case, right? And same as with array B. If our n represented 6, this would give us 6 executions, but it did not. Instead, it ran 3 plus 6 executions, which is 9. So that's why we have to have O of A plus B, where A represents array A and B represents array B. So be mindful of inputs of different sizes. Now let's cover our next big O, which is Linearithmic. And Linearithmic has a big O of O and log n. And as you probably can guess from the name and the big O, it's a combination of, or a product of linear and logarithmic. O of n for linear and O of log n for logarithmic. So it's like logarithmic, but it's multiplied by n. It is used to denote slower logarithmic function. So linearithmic is a function between linear and quadratic. Some examples are merge sort and quicksort. And I was thinking maybe I should use merge sort and quicksort as an example, but I guess if you're studying time complexity, you haven't gone that far. So I'll just use a arbitrary example. First thing I'm going to do is I'm going to make a for loop and let I is equal to 0 and I is going to be less than n, and I'm going to increment by 1 each time. And you probably can guess we have O of n multiplied by O of log n, and we're going to have a inner loop, and that's going to be let I is equal to 1, I is going to be less than n, and we're gonna multiply by 2 each time. And inside our loop, we're going to increase execution by 1. Okay, so we have our code, we have our results. When our input was 10, 40, 100, 700, 1,000, 10,000. So compared to our other big O's, you can already see our executions increasing. Now, we're more concerned about the big O. If you look at our for loops, well, does this one and this one look familiar to something else? Well, our outer loop is literally same as O of n, and that's our linear loop. Our inner loop is same as O of what? Log n, because we are halving the number of operations each time. And if you don't remember this, go back to logarithmic portion of the video to remind yourself. So we have O of n, and inside that we have O of log n. When you have a nested loop, you want to multiply whatever operations that you have. So knowing that, how do we figure out our big O? We have O1 here, O1 here, another O1, another O1. And you can change this to J. I should change it to J. J, and this one is also going to be J, just to make it simple, I guess. So we have 1, 2, 3, and 4. We have O of 4. And we have our outer loop, which is O of n. And what is this being multiplied by? Is multiplied by O of log n. And we know that we can get rid of our most insignificant term, which is constant. And can we get rid of our O of n? Well, we can't, because we are multiplying our big O's. So that's going to give us O of n and log n, which is linearithmic. If this isn't too clear, I think a better example might be merge sort and quicksort, and I'll probably make videos for that later. But for now, the most intuitive example that I can think of for linearithmic is this. Multiply O of n times O of log n, where O of n does half the number of operations each loop, because we are multiplying j by 2 each time. Now let's go over quadratic time complexity, and that has a big O of O n squared. So what is the definition? Quadratic time algorithm will increase directly proportional, so it sounds similar to linear, right? To the square of the input data or the input size. So it's going to be directly proportional to the square of the input data. So square is this, right? N to the second power. So if our input was 10, we would have 10 squared, which is 100. If the input was 100, that would be 100 squared, and 1,000 squared. So we're just squaring the number of inputs. And this one is our typical nested for loop, where we loop through everything each time. Let I is equal to 0, I is going to be less than n, and increment n by 1 each time. Same as before, we're going to have let j is equal to 0, j is going to be less than n, and increment j by 1 each time. Now we're going to do the same thing as always, increase execution. And as you can see our number of executions. So 10 squared is 100, 100 squared is 10,000, 1,000 squared is a million. So you can already see our number of executions increasing from constant, logarithmic, linear, linearithmic, and quadratic. Now let's calculate our big O, because that's our primary concern. Okay, we have, same as before, O of 1 here, another O of 1 here, variable I, O of 1, O of 1. So that's O of 4. Plus O of, well, our outer loop is what? Is O of n, because we loop through all the items in the array. and this one is also O of n because we loop through all the iterations until we reach j is less than n. So we have a nested loop, and so that's going to be O of n plus, not plus, times O of n. Like always, get rid of our non-dominant term and multiply O of n times O of n. And when you have the same number and when you multiply it, that's equal to O of n squared because we have two n's. So this is our final big O, and that's how we get quadratic time complexity. Now, I do have another example for quadratic time complexity, and if you look at our function, this kind of looks similar to what we did for linear time complexity. So we have inputs of different sizes. Again, we have array A and array B. Array A has a length of 3, array B has a length of 6. Now, I'm going to make a code and you figure out what the big O is going to be for this one. And if you have a solid or good grasp of what we did for inputs of different sizes for linear time complexity, I think you should be able to figure this out without any problems. I is going to be less than array A dot length, increment by 1 each time, and I'm going to make another loop. J is equal to 0. J is going to be less than array B dot length. So iterate through array B and increment index by 1 each time. And like always, just execution, increment by 1. So first of all, we have an output of 18. Is this the output that you expected? If that is so, that's great. But we are always more concerned about big O rather than what our execution is going to be. So what is our big O for this one? Well, I know that this is O of n because it iterates through a length of times, and I know that this is going to be O of n also. So what is our big O gonna be? It's going to be O of 4 because O1, 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 O1. We talked about that many times, and it's going to be O of n times O of n, which is, get rid of non-dominant term, we have O n squared. Well, if you thought it that way, is wrong like before, and you probably realized that it was wrong if you watched the video and paid attention. Well, why is it not O of n squared? Well, the reason is the length for this is 3. Length for this one, array B, is 6. Well, what is 6 squared gonna be? 6 squared is going to be 36. Is that represented in our quadratic? No, it's not, right? What if it was 3 squared? Well, 3 squared is 9. Is that represented in our quadratic function? No, it's not. So it must be something else. So going back to our first for loop, we iterate this array how many times? Length of array A times. So let's say that is represented by O of A. And same as our first one, our second one iterates to array B length of times. So that's going to be 6. And we're going to represent that with O of B. Do you see the pattern? So this is going to be O4 like always. And we have O of A and O of B. So we are going to have O of A times O of B because that's a nested loop, and we can get rid of our non-dominant term and we are left with O of A times O of B. So if we were to simplify that or rewrite that, it'll be O of A times B. And this is actually our big O. So when you think about big O, you have to consider inputs of different sizes, and that's exactly what we have. First one is 3, second one is 6. Where it's double of the first one. And if you think about it, O of A times B makes sense because 3 times 6 gives us 18, right? And this did 18 number of executions. If you were to write O of n squared, what would n be? Is it 3 or 6? Well, if it was 3, it doesn't make sense. If it was 6, it doesn't make sense. So always be mindful of inputs of different sizes because this one trips a lot of people. Now let's go for our exponential time complexity. And exponential time complexity has a big O of 2 to the n power, where n is the input size. Now execution will double with each new element for exponential time complexity. If you remember from logarithmic, what happens to logarithmic? Execution halves with each new element or loop. So think of exponential as the opposite of logarithmic. Now let's code our example. I'm going to make a for loop that I is equal to 0 and I is going to be less than math.power 2n So this is essentially doing 2 to the 10th power, and let's increment by 1 each time. And same as before, like always, increment execution by 1. Now, as you can see, our number of executions came out to be 1024. That's huge, right? If you remember from other time complexity, when you had an input size of, for example, linear, executions were 10. When it was quadratic, number of executions were 100. But now, when our input is 10, it runs 1024 times. So already it's getting bigger and bigger and bigger. Now let's figure out our big O. We have O1 here, O1 here, another O1 here. So that's going to be O of 3 plus, well, what is this going to be? Well, remember, math.pow 2 comma n is 2 to the nth power, which is 2 to the 10. And we can write this as O of 2 to the n. So it's going to be O of 2 to the n, and we know that we can get rid of our non-dominant term. So that's going to be O of 2 to the n for our example. Let's go over another example for exponential time complexity, and we're going to use Fibonacci numbers to do that. And again, exponential, think of it as opposite of logarithmic time complexity. As n increases, execution doubles each time, whereas logarithmic, it halves each time. And if you're not familiar with what Fibonacci numbers are just this. It starts out with 0 and 1 as the second number. What it's going to do is it's going to sum the previous two numbers to get the third one, and to get the fourth one is going to do sum of two previous, so 1 plus 1 is equal to 2. And the next one is going to be 1 plus 2 is equal to 3, 2 plus 3 is equal to 5, 3 plus 5 is equal to 8, 5 plus 8 is equal to 13, 8 plus 13 is 21, and this just keeps going. Now I have a pseudocode for Fibonacci, and let's code that first. So if n is less than or equal to 0, what we're going to do is we're just going to return 0, and else if n is equal to 1, we're going to return 1. That takes care of our pretty much base case, because first number has to be 0 and second number has to be 1. Now what we're going to do is we're going to recursively call Fibonacci function, and then we're going to add n minus 1 and n minus 2. Remember, in order to get this number, we have to do n minus 1, which is 3, plus n minus 2, which is 2. So 3 plus 2 is equal to 5. That's why we do n minus 1 and n minus 2 plus fib n minus 2. And if you do that, we get 13 as our number. Okay, so this is Fibonacci function, but why is this exponential function? Well, the reason is because when we call fib, what does our function do? It recursively calls fib how many times? 2 times. And let's go back to the definition of exponential. As n increases, the execution doubles each time. So each time we run this function, we're gonna call this 2 more times. It doubles, right? That's why this is an exponential function. For each call, we get another 2 calls, so it doubles. That's why this is, again, exponential. Now let's go over our last and slowest time complexity, which is factorial. And factorial has a O of n factorial. This exclamation mark is used to denote factorial, where n is a number. So what is the definition of factorial? Execution will increase n factorial with each element. And this is the definition of what factorial is. Factorial is product of all positive integers, so all positive numbers, less than or equal to a given positive number. So if we had 5 here, 5 factorial would be 5 times 4 times 3 times 2 times 1, which is equal to 120. And if we had 3 factorial, it would be 3 times 2 times 1, which is equal to 6. Now, just by comparing 5 factorial and 3 factorial, you can see that when we had an input size of 3, our execution or number was 6. When we have input size of 5, it's 120. So you can see that when this number increases or our input increases just a little, our number of executions or the number itself gets big really quickly. Okay, now I have my function. It has an input size of 7, and inside my function, I have a function called factorialize. So what this function is going to do is it's just going to factorialize a number for us. So let's code this first. I have my pseudocode here. Try it if you can. So if n is less than 0, all we're going to do is return 0. Oh, actually minus 1. And else if n is equal to 0 or n is equal to 1, what we're going to do is we're going to return 1. And these two base cases are pretty much the definition of what factorial is. So we can't have a number less than 0. So if we do get number less than 0, we're just going to return -1 to denote that this is invalid. And if we have n which is 0 or 1, what's 1 factorial? 1 factorial is 1, right? And you have to know that 0 factorial is also 1. So keep that in mind. That's why we have this line over here. And our last line of code, we're going to recursively run this function n times factorial n minus 1. So this is pretty much the definition of what factorial is. So if it was 5, we would have 5, and we will recursively run this function, passing in n minus 1, which would be 4, and so on and so forth. Okay, so we have our function which factorializes the number, and let's save that to a variable. I'm going to name it factorial, and it's going to be factorial of n. Okay, we have to name it something else. Let's just call it fact. Okay, that was happening because this shouldn't be factorial and this shouldn't be factorial. I hope you caught that mistake. It should be factorialized. So factorialize, and let's just call it factorial. I just like it that way. You can call it something else if you want because it's the same name as our function name. Okay, quick question. What would be the time complexity of our factorialized function? So think about it. We have our function, we have our if statements, and we have our recursive function. So this would be O of 1. This would be O of 1. How about this recursive line? What would this be? Well, if we have recursion, that's exponential, right? Well, actually, it's not because we are calling factorialized function just once for each call. So remember, exponential, you have to double the number of operations, whereas this one just calls factorialize just once. This is actually just O of n. So how does this function work? This is a little outside of what we want to talk about, but let's just be clear. So first is going to call factorialize with input of 4 if we pass in 4, and then is going to call factorialize 3, and then this is going to call factorialize 2, and this is going to call factorialize 1. And when we have factorialize 1, this is going to hit our base case, and then all these recursive cases are going to exit and finally return our result, the factorial number. Now, if you look at our recursive function factorialize, how many times did this run? So let's say that our input was 4. It ran 1, 2, 3, and 4 times, right? Not 2 to the 4 times. So 2 to the 4 would be exponential, but this one only ran 4 times. So this is O of n. Now let's get to our main part. So I'm saving this factorial number to this variable. So what is this gonna be? This is gonna be O of n, because this variable is essentially running this function, passing in the value n, and it's going through this function over here. So this is O of n. Now, what I'm going to do is I'm going to just make a for loop, not here. I'm going to make it here. Okay, for let I is equal to 0, I is going to be less than factorial, and increment by 1 each time. And what I'm gonna do is, like always, execution increment by 1. Okay, what happened to our number of execution is 5040 when we had only 7 as our input. So factorial can get really huge really fast. So we know that even when we have a small number of input, our factorial function is going to be really slow. Now, finally, our last big O. We have O1 here, another O1 here, another O1 here. This one isn't going to count because that's our O of n. So that's 1, 2, and 3. So O of 3. This one runs O of n times. So that's going to be O of n plus how many times does this for loop run? It runs n factorial number of times, right? Because our factorial is 5040. O of n factorial. And if you were to just console log factorial, to see what that number is. As you can see, it's 5040. So we are running this 7 factorial numbers of times, which is 5040. So we have O of n factorial. Okay, how can we simplify? O of 3 constant is non-dominant. Well, we have O of n. O of n is bigger than O of 3, but compared to factorial, this is nothing, right? When we have input of 7 for our linear, is going to run 7 times, whereas factorial is going to run 5040 times. So finally, our big O is going to be n factorial times. Now let's wrap up our time complexity. So we had time complexity constant being the fastest, factorial being the last, and these are our big O notations. And remember, this is really important. Simplifying big O notation, well, we know that it's always the worst case. Now, we did enough times to remove the constants. This is a really important one. Inputs of different size. You have to consider inputs of different size. Otherwise, your big O or time complexity might be off. And we want to get rid of non-dominants. So compared to x squared, when our x gets really large, 2x and 1000 is really nothing. So when we calculate our big O, we just drop these off and just look at the biggest term. First, big O was constant, and when we had an input of 1000, our output was just 1. And for logarithmic, when our input was 1000, our output was 10. And for linear, when our input was 1000, our output was the same, 1000. So you can already see how fast it grows. So from 1 to 10 to 1000. And next one is linearithmic. When we had an input of 1000 is 10,000 and linear was 1000. So it increased 10 times. Quadratic, the input is 1000. This is a million. So from 10,000, we came to a million. And now exponential. When our input was 10, remember previously we were working with 1,000. When our input was 10, now is 1024, 1024. I think if you can try exponential with an input of 1000, but I think your computer might freeze. I'm not sure. I think my mind freeze. I think that's why I didn't do it. So already when our input is 10, it's 1024. And the last one, factorial of 7. I mean, 7 is obviously less than 10, and 10 gave us 1024. Whereas factorial, when our input was 7, is giving us 5040 executions. That's huge. That's really slow. So as you can see from comparing different input sizes and how many times our function runs, you can tell how time complexity affects your code. So be sure to know all the concepts, especially simplifying big O, so that when you code, you know what you're doing. You know how fast or slow your code is working. So that's it for time complexity, and we'll go over space complexity next.